All right. So we had some tech difficulties, but we're going now. We lost like 30 minutes. So um I'll go through this. I'll have to accelerate some portions, but we'll be all right. So previously we've been going through this hands-on machine learning book. We're now chapters 15, 16. Ted went over convolutions, and then we decided to bundle up RNNs and transformers. They started talking about sequence processing, time series, language modeling stuff, and these are kind of logically grouped together. And we're trying to accelerate through the rest of the book. So I'll just touch on some of the key concepts here. So this is like concept map. Just understand, like if you get some of these keywords, then you've captured the essence of the chapter. So we'll talk a little bit about RNNs, recurrent neural networks. We'll talk about convolutional neural networks a tiny little bit, and then we'll talk about backpropagation through time, gated recurrent units, long short-term memory, attention, transformers, encoders, decoders, time series forecasting, the ARMA family of models, and just like solving unstable gradients a little bit. So the chapter starts by just going straight into recurrent neural networks. So we've looked at a bunch of stuff with neural networks the past few weeks, and what they introduced is this idea of recurrent neural networks. And the idea here is basically you're passing the output back to the input of the neurons. So this diagram, what it's showing is basically you have some input X, it's going into the unit, and then it's doing some operation, some nonlinearity, and then it's going out to Y, but it's also looping back to itself. So it outputs some value or some vector or some number, and it is looping back to itself. And so in this way, you can handle different sequences of inputs. So what they're showing here is you have X0, X1, X2, X3. So this is a different sequence of, it could be a time series signal, it could be a sequence of words, it could be a bunch of different pieces of something in order. And so the idea here, it's typically the way that this is handled is at the first step, you don't have any looped input, so you just start with a zero. So it gets one input that's a zero, one input that's the actual first time step. And then what it does is it will output some value and it passes that back to itself. And then at this point, instead of getting the zero, like we see over on the left-hand side, you get some actual value that was output from the model. And then X1 is the next time step, and that gets passed through. And so you can loop through this. And the nice thing about this is you can have kind of arbitrary length of inputs. So your regular like feed forward neural network, it has a certain fixed size. And with this, it can loop back on itself and you can say, okay, a sentence might have 3 words or it might have 7 words or it might have 32 words, can have variable lengths. And so with this, you can just say, okay, keep entering more words and just looping back on yourself. So that's kind of the idea of this recurrence. So passing back into itself, it can handle arbitrary length sequences. In reality, when you're doing training, you typically batch things to be the same size anyways. So if you have a 3-word sentence and a 15-word sentence, you might batch everything to be 15 all the time. But yeah, that's the idea. Is you can handle different shapes of input with these recurrent neural networks. And the nice thing about these is it's building up its representation over time. So it's going left to right in your reading order, and it's building up some vector understanding what's in your sentence or paragraph or something like that. But one of the things that they touched on was this concept of backpropagation through time. And so one of the difficult things with this configuration is you have one unit that's being applied multiple times. And so if you think about how the gradient flows through that, so you're doing all of these steps and then you get to the end and you make some prediction, you might only have one bit of label data at the end. So you make some classification and then you have to say, through all of those steps, how should I update my model in order to make a better model? So you're doing this training process where you say, roll through the whole thing and then make some prediction and then figure out what do I need to do in order to adjust the weights in order to make it more performant. And so this concept of backpropagation through time, what you're kind of doing is you're treating it as if each loop is like a new unit. It's a new neuron, when in reality, it's the same neuron that's being applied over and over and over again. And so what you do here is you say, I have a given output, I have a given input. How do I need to change those through all of the different time steps in order to optimize this model? So you might have something that has a sequence of 30, and then what you're doing is you're going at every time step, what do I need to adjust in the weight in order to get the better final outcome? So one of the things with recurrent neural networks is you can handle different kind of surfaces, different shapes of inputs and outputs. And I'll talk a little bit more about that later, but just understand you can have something where it's like variable length input and variable length output, or you can have variable length input and just a single output. So you can have different kind of densities of signal, saying you're supervised at every single time step or you're only supervised at the end. There's different shapes that that can take. And so this back propagation through time is how you kind of broadcast things if you don't have the full annotation of every time step. So that backprop through time is very important. It's how these things are actually trained. Without it, you couldn't train an RNN. So in the next section, they started talking about time series data, and this is one of the areas where RNNs, LSTMs, GRUs, all of those really shine. And so in time series, they showed some plots here. So this is just data over time, and the data that they're capturing is the amount of people riding the bus versus riding the train, basically. And so they're showing over time, okay, we have this pattern where more people are riding the bus during the week, not as many during the weekend. And so you can see there's this sort of seasonal pattern where you're saying, okay, Monday through Friday, there's more traffic. And then on the weekends, there's less so. And you can see this pattern repeats all throughout the basically. So this is very common in time series data. You have some pattern that might happen hourly or daily or monthly or annually. So you have these patterns that they repeat. Like that's just the way our lives work and the way data usually presents itself. So one of the things that they showed with this was that it's very powerful to just take your last time step. That's your like naive baseline is what they called it. So imagine you're trying to predict the ridership on these on the bus or the rail, and you could basically say, if I'm trying to predict what it's going to be tomorrow, I just take today's value because you know it's roughly going to be in the ballpark. Um, so you say like today 30,000 people rode the bus, tomorrow it's probably going to be a similar number. And if this number trends up a whole bunch over time, you're still kind of just taking the last known point, and so you'll probably end up roughly in the ballpark. So in certain cases, this will fail in a big way. So like if we look at this, the difference between Friday and Saturday, all of a sudden it's going to predict there's going to be 800,000 people again, when in reality there was 300,000 or something like that. So this naive baseline is a very good measuring stick for, is my model actually learning something useful? If your model doesn't beat that baseline, then it's probably not a very good model because it's not able to even do better than just like persist the last day's prediction. Um, so very powerful to use that just to measure like this is the bar that you have to beat to even be worth pursuing prediction. Um, One of the concepts that they talked about was stationary versus non-stationary. So there's some patterns that they just repeat forever. They just keep going, and you can say, okay, across 10 years, we've always had the same number of people coming into this office, for example. But then you have other things where it might just go up and up and up over time. So like if you look at stock prices and stuff like that, they're generally not stationary. They're not just repeating the same pattern over and over. The company does well and the price goes up over time. And so it makes it very difficult to predict because these models will look at the data and then they're trying to forecast into the future, but they're forecasting into regions that they've never encountered before. So if the model's never seen a stock that's over $10,000, then it's probably not going to behave well when it sees the stocks going up and up and up. So one of the tricks that people do with this is they detrend it, or they do temporal differencing. So the idea here is basically you just take the time steps and you just subtract them from each other. And you can do this at different granularities. So you can say, okay, instead of representing it as the actual stock price, represent it as how much has the stock price changed in the last hour, or in the last day, or in the last month. And so in that way, it's giving you different levels of detrending. So you can do it at different time scales, but you can do it also different amounts. So if you have something that's like highly non-stationary, it's like parabolic, it's just like going massively up, it's not staying stable, then you can apply this temporal differencing multiple times, and over time it will stabilize it out and make it more consistent. So for time series, the concept of stationary, non-stationary is very important. And then the way that a lot of people handle that is this detrending or temporal differencing. So you can do it with the temporal differencing, or what some people do is they find ways to capture these like seasonal patterns. So you can also do stuff where you remove the seasonality of the trend with stuff like daily patterns, hourly patterns, stuff like that. So there's a lot of different models that have been built on top of these concepts. So here's just an example of them showing this this time differencing. So in this, what they're doing is they're saying, here's this pattern, it repeats every week, and then if you look at this over 7-day differences, you can see like the difference between this Friday and last Friday is not that much. It's pretty constant, actually. So you can see some days it goes up, some days it goes down, but in general, it kind of stays central, because we know that it's not like some crazy pattern that's just going up and up. So that's kind of some of the key concepts of time series modeling. One of the things that they mentioned during the chapter was the different error measurement. So you might do mean absolute error. You're basically saying, what's the difference between my prediction and reality? You can square that. And then one of the ones that they were showing in their metrics was mean absolute percent error. And I have a funny story with that I like to tell. So I was doing a project where I was doing time series forecasting, and the project was trying to predict the energy price over time. And so energy price goes up and down depending on how much solar is there, how much coal is there, how much are people using. There's all of these factors that go into this. So I was working with this company, and the criteria that they gave me, they wanted to say, okay, if you can get within this band, then we'll give you X amount of dollars. You build a very accurate model that's worth a lot to us. And so the criteria that we set up was mean absolute percent error. And the thing that I didn't understand was that energy price can actually go zero and even negative. So if you have too much energy on the grid, then they will actually pay you to take energy off the grid. And so because the value is crossing over between zero, your percent error can go massive, because the difference between electricity being a penny and being negative 1 penny all of a sudden becomes a huge percentage error. So just warning about MAPE, that's a dangerous metric. So moving, yeah.
Oh, sorry. Sorry to interrupt. That's because you divide it by the actual amount, and if it's near zero, then is that why?
It's based on percentages. So if you have something that is 10 cents and you predict 11 cents, then you're only a small percent off. But if you have something that's 1 penny and you guess 2 pennies, all of a sudden your percentage is 100% off. You doubled what it was supposed to be. And so when you get closer and closer to zero, you have to be more and more precise. So it's like your prediction has to be within like a millionth of a penny for it to not get a really, really bad percentage error. So yeah, that's that's the danger of that metric. If you're in positive values and everything's fine, if it's always within a certain range, but that's one of the dangers of that metric. I'll pause for a second. Any other questions? I see a question about batching. So back on the RNN stuff. Um, so it's useful because the way that you typically handle these is you form everything as a matrix. So you say my batch has 16 and I want to concatenate them all and I want them to be the same size. One of the things that they mentioned in the chapter is you can have ragged tensors where you say this one has 8 and this one has 12 and this one has 13, and then you stack them all up and it can handle that. But generally, most of the libraries don't handle that very well. You want it to be kind of a static size. You want it to be 16 or you want it to be 32. So the way that people handle that is they define some max size and they say, okay, shove everything in here and just pad it wherever it's too short. Um, yeah, so that's the reason that people do that. So they'll do a batch of 16 and then they need to make everything the same length because when they pass it to TensorFlow or PyTorch, that's what it expects. I'll pause for any other questions. RNNs, time series. Okay. So they're showing they showed there's weekly trends, but also there's yearly seasonality. So one of the things that I was talking about is like you might have people tend to be using the bus more because now everyone's Ubering or something like that. So there's all these kinds of factors that you can see, like they change over time. Um, and so they're showing, before we showed a weekly differencing, now they're showing a 12-month difference. So like you could say maybe people ride the bus more in September. And so you say uh, subtract out the trends from the previous year, basically. So if you have multiple years of data, you can say look at the year before and just say separate that out, and then you can maybe level out some of the patterns that you see through years. Um, so time series stuff, one of the most popular models is this ARIMA. There's all these different variations on top of this. And the whole idea behind it is basically that we expect the future to be correlated with the past in certain ways. So if you're looking back an hour, that probably informs what's going to happen in the future. If you look back a day, that's probably going to inform the future. Um, and so with this, you can do certain things to remove seasonality. You can do things to like reach further into the future. So they didn't show this, but this is like one of the core concepts of ARIMA is just this concept of autocorrelation and partial autocorrelation. So the idea here is basically you can take a time step and then you say, look at previous time steps and how they correlate with the current time step, basically. So if you said take uh, the bus ridership from today and then measure how much does yesterday's correlate with it, and you do that for every time step from your data, you can say, okay, it correlates pretty well with yesterday, but it correlates even more with a week ago. So that's kind of this pattern that we can see here is we can see that the weekly pattern is very strong. So if we look a week ago, like every Friday, we have kind of similar ridership. And so this plot can kind of tell us that pattern showing like, okay, every week we have something that's highly related. But if we go further and further back, that trend is falling off. So if we go back 1 week, that's highly correlated. If we go back 2 weeks, that's slightly less correlated. If we go back 3 weeks, etc. So that's this pattern that we can see here. So 1 week ago, very informative. 16 weeks ago, maybe kind of informative, but not really. So this autocorrelation plot is very useful to kind of understand what is the actual like period and repetition of your data. It's useful to, if you don't know like it's a weekly pattern or monthly pattern or something like that, you can do one of these autocorrelation plots and it will show you, okay, the important thing is this certain time window.
Yeah. Just a quick comment about some of the time series stuff. I mean, we're focusing more on the deep learning, so like not super important. But when I was initially learning ML and started learning about this time series stuff, it's like, oh wow, there's all of this like new, separate, complicated stuff. And this is a slight oversimplification. But basically, after I learned more, it's just like, oh, okay, there's fancy data preparation. Like if you have weekly seasonality, you do this stuff where you like calculate the difference from 7 days ago or whatever. But like when it's all said and done, after you've done whatever the fancy data preparation is, it's linear regression. So I was like, oh, okay. That part I actually understand. It's just what sort of fancy data preparation. And so if you've heard of Facebook's profit model, it's like, yeah, it's the whatever or, ARIMA data preparation, but instead of having just seasonality that's like 7 day, month, year stuff, they also have an extra variable that's like, is this a holiday? And they have hard coded, like for the US holidays are July 4th and Thanksgiving and whatever, so that you don't have like this terrible prediction just because, oh, Thanksgiving's a Thursday. I'm expecting like lots of bus riders. And like, why is it all of a sudden there's no bus riders or whatever? Right. And so, like, when you get down to, again, slight oversimplification, but it's just like a bunch of fancy data prep and then it's just linear regression, nothing fancy.
Yeah, they had a decent amount in the book that was just preparation of the data. So it is important to understand that and know how you prepare these things. Like how would you make that autocorrelation plot? How would you prepare data for training, for example? So they showed the different methods of like you can do sliding windows, you can do random sampling of the windows and stuff like that. It's all very important, but it's not as core to the like actual algorithms. Most people can kind of figure out reasonable ways to do things. With time series, it's always a bit more tricky to properly prepare the data and validate and make sure you're not like looking at future time steps and stuff like that. But it's kind of just like once you dig into your data, you figure out how to handle it. It's not like there's some like constant principles that you need to learn. Um, so moving on to back to RNNs and how they apply to this time series stuff. So RNNs, I was mentioning, can kind of take different forms. So we can have a sequence of inputs. So you can say, I have a whole bunch of time steps, and then at the end, I just want to output a single prediction. So in the book, they mention like sentiment classification. So if you think of a sentence as a sequence of words, what you can do is you can read all of the words and then at the end you say positive review, negative review, or something like that. And so in that sequence, you're not making an output for every single word. You're just saying, I read the whole sentence. Here's my final output. Here's my assessment of that entire sequence. The other form that you can take is you can have a sequence of inputs and then you can also have a sequence of outputs. So like in what we were just seeing with the ridership, what you could do is you could say, I take in a sequence of the past 7 days and then I try to predict the next 7 days or something like that. So you can have variable length input, variable length output. It can be single or it can be a whole sequence. You can also have single input and then a sequence of outputs. That's not as common, but you can do all of these different forms with RNNs. Um, so what we've looked at in these plots, you could do one model for buses and one model for rails. But one of the nice things about RNNs is you can actually do both at the same time. So you could have one model that looks at both the bus and the rail variables, processes them, interacts them in any number of ways, and then also outputs a sequence of both of those. So it can be single variable or it can be multivariable. That's one of the beautiful things about RNNs is you can kind of merge multiple time series into one. So one of the techniques that they talked about was if you're training these to output one time step at a time or a few time steps at a time, what you can do is you can pass those predictions back into the model. So the model's trained to loop back on itself. So when you do this, then in the future, you can say, okay, just keep looping and just keep consuming your own output. And then what that will do is it can just keep forecasting into the future. So if you didn't train it to do that, it's probably not going to do very well, but it is capable of doing that. So one of the things that they were showing is they train this model, it processes this sequence, and then it outputs one prediction, and then it adds that to its that sequence of inputs, and then it says, okay, guess the next one, guess the next one, guess the next one. So in this, we can see that the predictions are the red and the labels are the blue. And what it's doing is it's saying, just keep continuing its prediction. So this is very useful to do. It's nice that it's flexible to be able to do that. But the danger of that is you're just accumulating error over time. So if on day one, you're off by 1%, then that 1% gets passed to the model. And then if it adds 1% on top of that, then it just keeps going further and further and further from the truth. So typically you don't want to, you can't say, okay, I trained my model to make daily forecasts, and then now I'm extending it to take, to go all the way to a year. It's probably not going to be able to do that. There's a question about anomalies. It's very difficult in time series stuff to handle like true outliers. So like one of the ones that was very prevalent, everyone was doing modeling of COVID, like the number of instances of COVID. And that was very difficult to model because you were getting varying amounts of information from all these different sources. And then you're getting this thing that has never happened before. So no one had a good model that could actually forecast what's the growth of this going to be. So what people were doing was they would say, okay, train a RNN on this, and then they check on its predictions a week later, and it was like it was off by an order of magnitude. They got all of these things wrong, and then what ended up being the most accurate was people just kind of like parametrically saying like, here's what the spread factor is, here's what we expect it to be in the next few days, because the RNN was no good at like understanding like this is an anomalous event. We've had years of zero, and then all of a sudden it curves up like crazy. So RNN's not very good at anomalies. So what we've looked at so far is the simple RNN. So in that setup, it's just looping back on itself. So it has some like internal state vector, and it's passing back to itself, and it's just saying loop, 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 loop. But what people figured out was this was very bad at maintaining information. So if you needed to keep something for any period of time, so if you have a long sentence and it's like describing some scene, and then you have to remember, oh yeah, I was talking about a dog at the beginning or something, it won't be able to maintain that information through the entire sequence. And so people kind of came to two different similar solutions, and one of them is LSTM, and one of them is GRU, or gated recurrent unit. And basically the idea here, they have various gates here. But the idea is, instead of just looping through everything, you want to like store some little bit of information. You want to store some vectors saying, capture this information and hold it until later. This is probably important. I want to store some information, and then later I can draw it back out and then use it whenever it's necessary. So the idea here is basically there's one forget gate, and the idea here is it can kind of erase some information from that memory. The input gate is when you want to add some new information to that memory. The output gate is when you want to use that memory again. So imagine you're going through a sentence, and then you're like, the dog was chasing the cat. It was running very fast. And then you go through, it stores something about dog, stores something about cat, and then it goes to it, and it says like, oh, I need to remember what it is referring to. Like, what are the different subjects that could be in here? And then it goes and it says, okay, retrieve that information about dog, because it thinks that was the one that was. It doesn't exactly work like that in reality, but that's kind of the idea. Is you want to be able to store some information, and in the simple RNN setup, it's very, very difficult for the system to persist pieces of information. And so this LSTM GRU setup is basically a buffer to be able to like store something for a little bit and then pull it back out later.
Quick color comment. So like again, this is a slight oversimplification, but you can just think that a regular RNN, it's just going to do a constant attenuation of everything it's seen before in order to not like overflow, right? So I just think like, oh, whatever I've seen before, I multiply it by 0.9 and I add in the word that I just saw. All right. And then with what Ryan said with this LSTM, if the input is something really unimportant like then maybe you use 0.99 and keep almost everything of what you saw before. And if you see a more interesting word, then you have to, squeeze it in there. So the key thing is that the LSTM is conditional on what your current input is. The RNN, it is always applying the same amount of forgetting, no matter what your current input is. And I don't think we're really going to get to it in these chapters in the book, but this is the fundamental thing that people who are doing LLM research are working on, is how can I make the LLM, the attention, more efficient, conditioned on what the current word is, to be smarter about what to forget, what to remember. That's like the fundamental problem in NLP.
Yeah. So the like general wisdom at the time was like a basic RNN, you might be able to hold some information for 10 time steps. Like it's just physically hard for the model to maintain anything for any amount of time. And then the general idea that people had was with LSTMs and GRUs that might extend it 10x. So you might be able to hold something for 100 time steps or 200 time steps, but it definitely didn't work for like 1,000. If you had a very long paragraph and it's all talking about one thing, it's not going to be able to retrieve something all the way from the beginning and use it all the way at the end. It could not maintain it, even with this gating mechanism, even trying to store that information. It wasn't able to actually hold something in its like sort of pseudo memory for that long. So that was kind of the wisdom at the time, was like, okay, if you have anything very long sequence, that's the best you can do, but it's still not that good. So if you have very long sequences, it's probably going to break down in some way. So one of the things that people do in order to get around that is they use CNN, convolutional neural networks, like Ted talked about previously. So one of the things that you can do is if you have a sequence that has 1,000 or 10,000 or something like that, you process it with a CNN with different step sizes or different filter sizes, different dilation. There's all these different tricks that you can do to take a CNN and then reduce down the time steps. So if you have a sequence that's 10,000 time steps, like you would probably have with audio, audio is sampled very quickly. It has tiny little time slices. And if you say it takes 10,000 steps of this audio recording just to represent a word, then it's very difficult for an LSTM to say all the way from the beginning to the end, okay, they said the word dog, like that's already too long for it. So what people would do is they would take CNNs and they would say, okay, process this a whole bunch and take it from 10,000 down to 1,000 or even less maybe, and then they pass it through the RNN, and then the RNN can handle that reduced sequence length. So CNNs on their own can be used to process time series data, but LSTMs, GRUs are still kind of the dominant for that. So after we'll talk about transformers, but it's still like CNNs, RNNs, LSTMs, GRUs are all still very commonly used in many different scenarios. So one of the setups that they showed was this WaveNet architecture. At the time, it was a big deal. At this point, no one really uses it. It was like, oh, this amazing state-of-the-art thing. But for that problem that I was talking about, where you're trying to understand audio, you're trying to transcribe it, was a very big deal because this was able to look at much bigger timescales than had previously been done. And the way that they did this was with different levels of dilation. So what they're doing is they're doing 1D convolutions at kind of different timescales. So one of them is looking very granular, one of them is looking a little bit bigger, a little bit bigger, bigger, and then it can get this sort of global view of that word someone was saying. So a lot of this has been replaced by other stuff, but it was very powerful that someone could just do convolutions at these different timescales, and then all of a sudden it became a great speech recognition system. So one of the next sections, what they were talking about was a character RNN. So the idea here was you have some text, and the way that they wanted to represent it was every character was its own little piece. So instead of splitting it by words, they split it by characters. So it's just a letter C, H, A, R. They would split up words like that. And then the sequence processing that they're trying to do is they're trying to do predict the next character. So if you have the word C, A, and then it predicts the next letter is T, then it made the word cat. And so RNNs are very powerful at this text processing stuff. And so they showed this configuration where they basically said, train a model to just always predict the next letter. And this is very similar to the way our large language models are built now. It's just they're at the token level instead of the character level. So Ted was talking a little bit about the like time series prep. This is one of those things that they were showing is like when you're doing it with sentences and words and stuff, it's kind of the same time series preparation that you need to do, where you're saying take windows of words or take sentences or take some other unit and take windows of them and then say, okay, given the last 14 characters, predict the next one, for example. So when you're preparing your data, you might have to kind of like chunk it up in little batches and then prepare it in the correct way in order to handle it with these models. So they showed this setup and it looks very simple, but if you look at the actual details behind it, it's kind of complicated. So they showed this model definition, and what it's showing is the embedding layer. And what this does is it takes the IDs or the characters and turns them into an actual embedding. So if you have the letter C, what it's doing is it's looking up and saying, what's my embedding for the letter C, for example. So it's making this lookup table. That's the number of characters that you have times the embedding size that you define. So for us, we have 26 letters, and then we say we want to make it a 16-dimension embedding. And then you're passing through this gated recurrent unit. And then at the end, it has to classify which of these characters is the most likely outcome. So this GRU, it's one line of code, but it's this whole chunk here. So very easy to just go take that, use it in Keras or TensorFlow or PyTorch. It's very easy to just go plug that piece in somewhere. You don't have to know all of the math of all of the gates and everything. So they built up this example, and then they showed we can actually build a decently smart character predictor. And then the next example that they were showing was sentiment analysis. So the sentiment analysis, it's that it was a very, very common task that everyone kind of started their NLP journey with. And with that, what you would do is you have reviews from IMDb or Yelp or something. You read the text of the review, and then you just basically say, classify, was this positive, was this negative? And that was a common thing that people like tried to see if they could build strong language understanding out of that. And at the time, it was like we have these state of the art LSTM, but then you go look at the predictions, and it's like the person said they hated the movie, and you said positive. Why did you do that? Like, it was kind of embarrassingly bad in hindsight, because now we have these large language models where it's like it would get 100% on all of these things. Um, so in the sentiment analysis problem, it's different from the character RNN. So the character RNN, it's taking a sequence and then it's making one output, and then it's extending, and you can say guess more characters, guess more characters. For the sentiment analysis, what it's doing is it's saying take in this sequence and then just guess one prediction, and then it's just done. It's just positive, negative, basically. So with this, they did it character wise, but what a lot of people have found is even better than that. There's stuff like sentence piece and word piece and byte pair encoding. These are all different techniques of grouping up letters to form tokens in a certain way. So you might have very common like co-occurrence of letters. The one that I always use is like ology. If you understand what the word ology means, that's useful for understanding language. There's many different roots like that and other common words that you might want to represent as a single token. So building up a bigger vocabulary actually makes your model more powerful, and it makes it so that your sequences are much shorter. If you had to guess everything character by character, that means your sequence is much, much longer. So if you can do a whole like one of the examples they were showing was if you make New York one token, you just saved yourself that many characters. You don't have to loop through the model that many times. You have an actual token that just says this is New York. Just do one prediction, and that represents the whole thing. So the typical path through the text handling is you would take your text and then you do some form of tokenization. So in the example they gave with the character RNN, this would be just split on every single character, or you can use sentence piece, word piece, byte pair encoding. There's all these different techniques, but typically the idea is we need to take this text and then reduce it down into some like discrete form. And then you might do some form of padding on top of this. If you have a lot of text, then you say, okay, make sure all of my sequences are under 512 words, for example. And then you pad everything to be one big matrix that you can handle. And then after that, you go from your tokens to your embedding. So you look up and you say, okay, this is the word New York. Go find the vector that represents New York and then input that to my model. And then after that, you actually pass that to your model. So you have your RNN or LSTM or CNN or whatever you pass your inputs to. That's typically the flow though. And then your model at the end will output whatever you construct it to. So it can be single output, many outputs, one output for every word, for example. There's many different things that you can do. So we've talked about it quite a bit, but the big rough edge to this is that like time series, it's pretty easy to constrain and say, I'm always going to do the last 30 days. But for text, it's much more ragged. Like you have one sentence that has a lot, one sentence that has a little, and you have all this variation. So with text, it's kind of more of a difficulty than with time series stuff when you need to chunk in all these random different sizes. So the embedding layer, this is the layer that's saying look up the word cat and then have some representation of that. You can train that from scratch on your own. So you adjust the embedding parameters and you hope that you got some good representation of cat. But the difficulty of that is for your specific task, you probably don't actually have that much data. So you have to learn these embeddings like on the fly while you're doing whatever your task is. So in reality, what a lot of people do is they reuse pre-trained embeddings, pre-trained vectors. So there's certain different word2vec, glove, fast text. There's a few other ones. But what you do is you just download these, and someone has pre-trained these to be very strong representations of words. So for like word2vec, Google went and said, okay, download all the text on the internet and just do like kind of similar to that char RNN thing, where they're just saying, keep guessing the missing text, and then with that, it builds up a strong embedding, and then you can go reuse that. And so that's very powerful when you have a task where it's like, the word cat only occurred once in my data set, so I can't really grow a good embedding out of that. But the word cat is on the internet thousands of times. So they built a good representation of it, and then you can go reuse it. So there was a point where all of the text processing stuff was reliant on these embeddings that you would download. So you would just say, okay, Google made good ones. I'm going to go use those and then apply them to my certain problem. So now what's happened is these word embeddings have been kind of replaced by entire models. So then came BERT and all of the models after it. And what these did is they kind of went away with like, I'm going to have embeddings for all these different words. I'm going to have a general like embedding model. And what this is going to do is it's going to take these words and then make a strong embedding from them. And you borrow that whole model instead of just the embedding layer, for example. I'll pause for questions there if anyone has any. Okay. So far, the format that things have taken is we have the different forms of input and output that you can do, but they're highly coupled. So if you have a sequence of inputs, then you might have a sequence of outputs that's the same length, for example. But this encoder-decoder architecture kind of breaks away from that. So the idea of the encoder-decoder is you might have something that goes like, okay, I take my whole sequence of text and then I condense that down to a single vector, and then I take that vector and I expand it back out to a full sequence of text. So this showed to be very, very powerful in neural machine translation. So if you wanted to translate something automatically from English to Spanish, for example, then it's very difficult for a model to just look at it one word at a time and say, I'm going to translate each of these words as they come, because it actually needs more context than that. It might need to read the entire sentence in order to do like a full translation of it. It won't know exactly the context that word is being used in. So what people did is they figured out we can take this input text, encode it in some way, and then after that, we have like the condensed version of that entire sentence, and then go translate it to back to text. So this is what one of these systems might look like. So they point out two different pieces. So they have the encoder and they have the decoder. So this encoder, what it's doing, it's got the text, I like soccer, and they're turning each of these into indexes. So they're saying I is just word number 3 in our lookup table, and then they're turning that into some embedding that becomes the first element in the sequence. And then what they're saying is we go through this RNN, we're going loop through X0, X1, X2, and then at the end it's read the whole sentence, I like soccer, and then at the end it outputs some vector. And typically what we were doing in the past was we would just keep looping back on itself. But what we do here is we actually pass it to the decoder. So what this decoder is doing is now it has a vector that represents this entire sentence, and then it's going and saying, I'm going to loop through and just go until I hit an end of sequence token. So it's just looping, looping, looping. And so it says, okay, I see the word I'm going to translate that to me. And then it does this whole sequence. So the nice thing about this is it separates how long your input and how long your output has to be, but it also makes it so that your part that's like actually outputting the text is looking at the whole sequence first. Um, so this is very powerful. Like at the time, it just blew everything away in terms of translation. So in the past, we had fairly simple like translation methods, and they weren't that good. And then all of a sudden, encoder decoder stuff started showing up, and all of a sudden, the error rates and the quality of translation went much better. Um, so what we've seen so far with RNNs is just going left to right through the sequence. But what people showed was even better than that was actually doing it bidirectionally. So you essentially do one forward pass going left to right, and then you also have another pass going right to left. And so in that way, you have the kind of representation from the left side building up that memory, and then you have the opposite saying build up your memory from the right side, and then you can concatenate those together, and then you have a bidirectional representation. um, so this showed to be very powerful as well. It's a very simple trick, just basically saying I'm going to read it forwards and I'm going to read it backwards, but it turned out to be very valuable to be able to do that in the opposite order. One danger of this is it makes it that it's no longer causal. So when you're doing it left to right, it never sees future information. But when you do it in both directions, all of a sudden you're seeing future information as well. In an encoder decoder setup, it doesn't matter because it was seeing the whole thing anyway. But if you're doing like time series stuff, you don't want it to leak the future information back to it. Um, so one of the things that they showed was that it's common to do sampling rather than hard outputs. So when we're back here and it's saying I'm gonna guess these words, it has a certain word that is its favorite, and we could just always pick that every single time. So you could do the argmax, say this is the model's favorite prediction, or what a lot of people do is some form of sampling. So they say the model output 80% this and 10% this and 5% that. And then it's saying I'm going to use those probabilities in order to determine how I sample text out of that. And so in that way, you can get more variety out of your text. And then also your text is less likely to get stuck on something. So one of the common problems with these kinds of models is it will output some word and then it just kind of breaks and it just says, oh, I like the word the, and then it just says the, and it just keeps going. So this sampling can sometimes prevent that. And there's a whole bunch of different techniques in terms of sampling and how you actually like constrain the model to only look at certain tokens and stuff like that. But one of the techniques that they show is called beam search. And the idea here is basically we can look at the combination of probabilities. So if I output this word, I can do multiple predictions forward and just kind of simulate what if I go with this word, what if I go with that word, what if I go with this other word, and then you can go multiple branching steps forward and then say, okay, this one seems like it's the most overall confident. So at an early step, you might actually say, okay, this one, its probability is a little bit lower, but it leads me to a path that has higher probability in the end. It's not that common for people to do beam search anymore because the models are so expensive to run. But it is a common technique for people to kind of say, okay, branch 3 possible options, just keep doing that like maybe 2 or 3 steps into the future, and then say what's the most likely sequence given the probabilities that it's putting. Because sometimes it outputs very confidently on one word, but then if you look at like it drove itself into a dead end in some way. So that's one of the nice things about this beam search is it's kind of looking forward and saying what's the path to to a reasonable outcome. Pause for questions. Okay. So, yeah, someone online.
Oh, can you hear me?
Yep.
How dependent is Beam Search on feedback from, I guess, a user? Because if it's using a lot of different probabilities to know which one to keep, to know that it's the right answer and to keep using that pattern, doesn't it require a lot of feedback from, I guess, a user or a person who's reading it for that situation?
So the beam search is just purely based on the model's confidence. So it doesn't actually take any feedback from the user. So what it's doing is it's saying, here's my 5 favorite words, for example, and then it's saying move forward with those 5 different words, and then just looking at its own probability and saying which is the most likely path. So there's no human feedback in this process. It's just kind of the model itself simulating what future step is most likely.
Mhm. Thank you.
Yeah.
If you want, I can give like a concrete example. So, gosh, I'm trying to remember exactly how it works, but like, so imagine that you ask ChatGPT some question and you're asking it like, what city is the best for, I don't know, whatever, and in its brain it's thinking, oh, the top 5 cities are San Diego, San Francisco, San Jose, but each of them's only like 20%. And then the next city that it has is Los Angeles and it's 40%, right? Intuitively, we would say like, oh, the 40%, that's the best city. That's the one that you should most likely output. But if you're looking at it just one word at a time, it's like, well, LOS is 40% and SAN is 60%. So it's actually far more likely to spit out San and then be forced to say San Diego, San Francisco, or San Jose. Beam search would not do that. It would go a little further and it would say, oh, Los Angeles combined 2 words is 40%, and San Francisco's 20, San Jose's 20, San Francisco's 20. And so then the beam search would pick um, Los Angeles far more likely, appropriately 40% of the time, instead of picking it, only a very small amount of the time because the sand kept winning for bad reasons.
Yeah, that's a good example. So getting to attention, we only have not that many minutes, and attention is pretty complicated. So I'll try my best to summarize this. So one of the big things with RNNs we talked about was it struggled to like maintain information for a long time. So if you wanted more than 100 tokens of like information retention, it was very bad at that. And so one of the ways around this was attention. And so what attention did was basically saying, don't worry about maintaining information. I'm going to give you the entire thing. So give it the entire sequence, and then it's choosing what it focuses on at a given time. So give it the whole paragraph, and then it chooses what to look at a single time instead of looping on itself. So the idea here was kind of similar to the embedding stuff. Was instead of embedding just in one way, you would embed a query, a key, and a value. And kind of the loose way I would describe it is you have these 3 different pieces, and you're at a certain time step, you're saying, okay, here's my query, I'm looking for some information, and then what it's doing is measuring its similarity to some key, and then it's saying this key is associated with some value, return that information. So like in my example before where you're saying like the cat chased the dog, it was blah blah blah, it might look at both cat and dog, and it gets some weight towards it, saying, I'm going to capture some information from that. So what it's doing is it's saying, I have a query that's the word it, and it is going to look at cat and dog a little bit, maybe some more towards cat, maybe some more towards dog. Hard to say, but then what it's doing is it's saying these are similar. This looks like it has the information that I need, and then it will take the value forward that's associated with that key. So there's this kind of these three pieces that all fit together. There's a lot that you can study with this. People have tried many different things with this, so I can't go in like such great detail. But one of the things with this is when you do it that way, where you're saying, I'm just going to compare against all of the other words in this paragraph, then the difficulty is you have no notion of direction anymore. So in our RNN, we're saying we passed it the first word, then we passed it the second word, and it's just looping, looping, looping. And so it has some kind of like implicit understanding of the ordering of words. When you do this with the transformer, it looks at the whole thing at once and it compares all the words to all the other words. And it doesn't have a notion of the ordering. So what people have to do is they add some positional embedding. And what this is doing is it's basically telling you where in the sequence did this actually occur. So there's some embedding that's saying this is a token that happened at word 0. This is a token that happened at word 1, so it's close to it. This is a word that happened at word 257, so it's very far away. It's probably not as related. And the way people configure these is they make these position embeddings, so it kind of biases the transformer to look at the words that are close to each other because their positional embeddings are similar. I mentioned this scale dot product attention is like the kind of current modern form that a lot of people do this in. I wouldn't worry too much about the details. Like if you're a researcher, this is very important to know, but just kind of understand the intuition behind attention. So we have the queries, the keys, and the values. And this is basically saying measure the similarity between the queries and the keys, and then give some weighting to the values based on that. So this is the very common transformer architecture. So you'll see this diagram like all over the place. It's shown a lot in blogs and all these papers that reference it. This is the original diagram for BERT, which is one of the first popular models that used this attention mechanism, and specifically multi-head attention, which is one of the variants of attention. So here's a diagram showing this attention mechanism. So this is like what I was talking about, where you have it is looking for some information, and then it's getting some weighted input from all the different words in the sentence. So people do a lot of visualizations like this, where they're basically saying like, okay, what is it paying attention to? What is it getting its weighted input from? There's two very popular blogs that I wanted to show. So one of them is this illustrated transformer. So this is a very important blog that this Jay Alamar guy put together, and it shows this whole thing in great detail. So he breaks down the encoder decoder stuff. He talks about the attention mechanism. So if you want to like understand this well, I think this is where I would start, is looking at his diagrams and trying to understand the various different pieces to this. So very important blog. There's two different pieces. There's the annotated transformer and the illustrated transformer. The annotated transformer has more code and like some of the details behind it, and the illustrated one has more like diagrams and showing you like what's the ideas behind it. So depending on whether you're like code focused or concept focused, I would point at slightly different ones. So very good resources.
Yeah, super quick comment. Those are super, super awesome, both of those. When you hear people talk about the transformer, the paper they cite is Attention is All You Need. That was a paper about machine translation, so translating English to French or something like that. And the architecture they use for that is the thing that Ryan mentioned, where you have encoder decoder, or sometimes they call it sequence to sequence. ChatGPT does not use that architecture. It's actually a slightly simpler architecture. But so just know that if like you really want to understand how like Gemini, Claude, what they look like under the hood, you kind of have this compromise. You need to look at something newer, but a lot of the newer stuff isn't just as awesome as the original stuff. But just don't be confused that these are super amazing, but it's not showing you the exact architecture. If you're now reading a research paper about, oh, we're going to modify Quen, Quen doesn't look exactly like that because all these models are actually a little bit different from the original transformer.
Yeah, so this diagram is for BERT, and BERT is this famous model, also came out of Google, and this was one of the like turning points that made transformers very popular. The way that this was trained was it was doing fill in the middle, basically. So you have some paragraph of text from the web, and what they did is they just said mask off random pieces of it, and then said train this model in order to fill in the blanks. So it always had a sequence of 512 words, 512 tokens, and then it said mask off 15% of these and predict what used to be there. So in this way, they could do it on the entire internet, and the model just got very, very good at understanding where do words typically go. And in that way, it built these awesome embeddings that understood a whole lot, and then could transfer it to all kinds of different tasks. So one of my like earliest projects, I was doing a Kaggle competition, and we spent months and months training all these LSTM, GRU, all the fancy stuff with the different embeddings that we could download. And our solution was this massive like 30 different models all glued together. And then BERT came out like a year after that, and people just said, okay, I take BERT and I get 5% better than like all of this crap that you guys put together. So that was how good it was like we did all of this work and we get to like 94% accuracy, and then BERT comes along and it's like I get 97 and I didn't even like try. It's just like the model's smart on its own. So BERT was very, very powerful. It was a step change in terms of capability. Um, so it was trained on two different objectives. So one of them was basically fill in the blanks, and then the other one was guess, is this next sentence the one that actually followed on the internet? So you took a web page and then you said, okay, take this sentence, take that sentence, and then randomly swap it sometimes. So you actually got like this one was an article about sports, and then this one is an article about finance. And then it would predict, did these actually occur after each other, or are they completely unrelated sentences? In the end, people have kind of figured out that next sentence prediction was not useful. It's not like something that people still use, but that was the original model was configured in that way. Now everyone just focuses on the either fill in the blank or guess the next token. That's kind of the two different modes that people will go into. So at the end of the chapter, this is the final little bit. They talked a little bit about how vision transformers have also taken over. So we think of like text as kind of obviously a sequence, time series is obviously a sequence, but people figured out we can also apply these to vision as well. So vision, we don't think of it as a sequence, but the way that people could break it up, as they said, well, actually we can break up the images into little patches, and then it's kind of a sequence. It's just a sequence of patches, but we have to have some sort of 2D embedding. So our regular positional embedding is just saying left to right. Our words are going to follow this order, but then when you do a 2D embedding, you're just basically saying, okay, this word is above that word, or this token is above that token, for example. So they ended the chapter talking about vision transformers and how those have taken over. When they published the book, it was less so true than now. Like even more now, vision transformers are the dominant way of handling things. So that's it. That's all I have for the chapter. I can pause for questions or anything. Yeah.
Are the vision transformers what diffusion and stable diffusion are based on? Or
I believe so. I haven't looked specifically at the stable diffusion architecture. Most of those kinds of things are transformer based in some way now. Like I
Yeah.
know
At the end of the day, they usually have a small portion that's processing the image. And then they have the diffusion part, which is actually separate from just processing the input. So whether the processing of the input is CNNs or vision transformer doesn't really matter. And then the diffusion part, early ones were UNets and new ones are transformers. So the two parts are actually kind of independent levers that you can decide what you want. Other questions?
yeah.
For like a model like BERT, like how do you pull the embeddings like out of that after you've trained it so that other people can use them?
So that was something that was very confusing to me early on. So you can't you can just use the embedding layer, but that's not particularly valuable. So in the previous setups, you would basically say, here's word to vec, I download this big file, and it's just the mapping between like cat gets this vector and with BERT, you kind of have to keep the whole model, because what the model is doing is it's taking your words, it's embedding them, and then it's doing the interaction with all of the embeddings to get the proper like contextualized embedding. So what most people do is they just use BERT itself and then they say fine tune the last layer, or you can take the like final embedding out of the last layer of the model and then train your own thing on top of it. But you can't use BERT directly as like just turn words into embeddings. It's a little bit more complicated.
All right, we have a hand raised. So Jock, and then in the room next.
I had a question about forecasting. There was a statement in the book. I want to read it really quick. It's a really short like paragraph. When dealing with time series, you generally want to split across time. However, in some cases, you may not be able to split along other dimensions, which will give you a longer time period to train on. For example, if you have data across the financial health of 10,000 companies from 2001 to 2019, you might be able to split this data across the different companies. It's very likely that many of these companies will be strongly correlated, though. And if you have correlated companies across the training set and the test set, your test set will not be as useful as its measure of the generalization error, which will be optimically biased. My question is, when you train, don't you want to have it train on correlated? It says it's not, but don't you want to have the training set on correlated companies in this example? I'm not sure if that makes sense. It doesn't make
Yeah.
sense to me.
Yeah, so you can kind of optimize for two different things. So you can optimize for trying to predict for new companies, or you can optimize for trying to predict into the future. So you can split your data in the two different ways. So say you have all of the companies on the stock exchange. You can say, I'm going to train on 90% of the companies and then measure how do I perform on the last 10% of the companies. Or you can say, I'm going to train on all of the companies up until 2020, and then I'm going to see how does this model perform on 2021. Those are kind of your two split options. And it's just basically saying, are you going to measure your performance in terms of how do you generalize to new companies, or how do you generalize to future time? And so it really just depends on what you're trying to measure and what you're trying to optimize for. Ideally, you would have some way of kind of doing both. Like you want to be able to understand a new company got put up on the stock exchange and its future time. So you want to measure its performance at both of these. But the difficult thing that they're trying to point out is that if you do the company split and you say, okay, I trained on my data from 2001 to 2019, some economic event happens in 2017, for example, then all of the companies will probably be impacted by that in some way. And so you're measuring that economic event more than you're probably measuring the like all the different companies. So you might be like biasing your model towards like there was some economic collapse, and so there was some big change that happened there. That's having a larger impact than just the new companies or the new time.
Okay, I think I got you. Thanks.
On the vision transformers, you mentioned that they operate on different patches. Should I think of those patches as, say, different regions of a single static image or different frames of a video sequence?
It can be both, actually. So people can configure them. The typical one is like you take your image and then you say take little 16 by 16 patches of the pixels. But what some people do, if you're like processing video or something, your patch could be include time as well. So you could have 16 by 16 by 8 frames of video or something like that. So you could say, look at this little chunk of pixels through time. So it can work both ways. The typical like vision transformer though that they're talking about is just saying take 16 by 16 pixels, cut those little patches out of the image, and then have it do the transformer on all of those little pieces. Yeah.
Any other questions? All right, cool. Thanks, Ryan. Thanks for also accommodating the late start and compressing things a little bit. I thought I would share one other practical example, just comparing RNNs to transformers. If you look at the diagrams, the little famous picture of the transformer doesn't really help you understand queries and keys or whatever, but sometimes you'll see these little square diagrams that have queries and keys, and they show the attention patterns and whatever. And I never found that was super duper helpful. Like it gave me a little bit of intuition, and then there's the newer intuition that people backed into, because when you're doing transformers, every time you add a word, okay, then your sequence gets longer, and that query is going to get dotted against every the keys for every word that's ever been, okay. But you've already seen all those words before, and you've already computed the keys for them, because in prior, when the sentence was shorter, you already saw those and you computed the keys. So they realized, oh, I don't actually really need to compute the keys over and over again. I can just cache them, and they'll be there when I want to do future calculations of queries with keys. Okay. So then they said, I'm going to build this thing, this key and value cache, this KV cache. And so as your sentence gets longer, as it gets one word longer at a time, the KV cache keeps growing by 1 for each thing. Okay. But this actually then gives a much better intuition for the difference between an RNN and a transformer. The RNN takes a little bit of memory to store its, or LSTM, takes a little bit of memory to store its state as you go from token to token. Okay. And so what you can do is you can call that little bit of memory the RNN KV cache. And the RNN KV cache is small, and it's the same size forever. So if you have 1,000 words, like Ryan was saying, it can't remember, past about 100. It's got this little memory, and it has to remember all 1,000 things it's ever seen. Transformer solves that problem, because what does it do? It just grows the size of its KV cache by a factor of 1,000 when you've seen 1,000 words. So from a how do you remember things perspective, it's really easy because it just says, I create this tape and it's infinitely long and I'm going to store everything I ever saw in there. Computationally, that's what researchers are trying to solve. Is now it gets super duper expensive when you give it 1,000,000 words of your large code base and you ask it to do some task. Now, every little thing it's doing, it's comparing against this 1,000,000 long memory tape, and it's just super expensive. So, so that's kind of the thing. So, um, this hardware optimization of having a KV cache actually, what I found, gave me a better intuition on really what the heck is the difference between RNN and the transformer. So the KV cache is this memory, and the queries is calculated for every new word that you see, and then you throw them away because you never reuse those. So I hope that helps. And then like for practical task, I imagine like, oh, a deck of cards has 52 cards in it. Theoretically, if I showed you 51 cards, you should be able to tell me with 100% accuracy what is the card that I'm holding in my hand that you haven't seen. Okay. An RNN would be like, I give you a little scrap of paper and you can write a 3-digit number on it, any number you want. You can think as hard as you want, and you can write down a 3-digit number. And I show you the cards one at a time. And after each card, you can think, and then write down a 3-digit number. Are you going to be able to tell me what the last card is after 51 cards? But if instead I said, you have a very large piece of paper, and after each card, you can write oh, and by the way, for the RNN, you write down a 3-digit number, and then after I show you the next card, I throw away the old 3-digit number that you wrote down. You can write down a new one, but you only get to keep one 3-digit number. The transformer, basically, it's like I give you a really big piece of paper and you can write down a 3-digit number for every card that you've ever seen. And so you can have 51 3-digit numbers, and you can spend as much time as you want examining those before you make your prediction. What is the last card? Well, obviously, you can then just write down the numbers, whatever, 1 through 52, and you just see which number's missing, right? So that's like the power of having this long piece of paper, this long memory. But also, you can imagine it might still take you a long time to figure out which of the numbers is missing, even though you've got the 51 of them written down. Like, oh, I don't think I saw 13. Oh, shoot. Nope, there's 13. Like, it'll take you a while to figure out, but you can, with enough computation, figure out which of the 52 numbers is missing. And that's a very simplistic analogy to the kinds of patterns that an LLM can learn, given this ability to just write down everything that it ever saw.
A matter of how long it takes you to look it up.
The RNN is not allowed to look at the cards it's seen before. Once they're gone, I show it to you and then I take it away.
Challenging with the CNN to when you have such a large cache, it computational.
Yeah. So the benefit is you can go back and you can stare at it and you can compute something, but if it weren't 52 cards, if it was 1,000,000 cards, it gets computationally expensive to refer back to all of them.
Is there a rule of thumb for when a sequence gets too long for an LSTM?
I think it depends on the nature of the data a little bit, like how much it's trying to store. But the rule of thumb was like over 1,000, it's probably not going to be able to maintain that information. So that wasn't that big of a deal when people were saying, I'm just going to give you a text sentence or paragraph, but then people started doing like, I'm going to do coding tasks with this and I need to look at like a big chunk of code, or like people doing stuff with like DNA and stuff, and they're like, my sequence needs to be 1,000,000. So LSTMs, like I would say in the hundreds or thousands, like optimistically, but beyond that, can't really maintain information that well.
So in terms of architecture, is the KV cache like stored on DRAM or something? How does it work?
Yeah. So where you store the KV cache is just a hardware optimization. So if you can store it on the GPU, that's the fastest.
Yeah.
And that's what people do in a simple, naive implementation. So if you're running something very small, a 3 billion model on your own computer with one processing, one GPU, one whatever, then yeah, that's all they're going to do is they're just going to store it on GPU. Hypothetically, you can offload part of it as it gets really big onto main memory, but then it gets slower to use it because it takes you longer to kind of like be shuffling it in and out of your GPU. And again, you can do more and more hardware tricks to try to, but the fundamental idea is if you're going to fully implement a transformer, then it needs access to every word it's ever seen before in the form of the KV cache. And if your code base is 1 million words, then technically speaking, there is no shortcut. It has to, in full attention, it has to be able to compute the similarity, the dot product between my current query and every word that ever has been seen before.
Thanks.
One of the speculative bets that some people are making right now is we've hit all of these different bottlenecks where it's like, oh, we need this much memory, we need this much bandwidth, we need this much compute. And one of the like next level bets people are taking is that we need bigger and faster storage because they think that we're going to get to the point where we go, we want more than 1 million, we want 100 million. And that's never going to fit in DRAM. So people are investing in like SanDisk and all these other companies saying, eventually we just want really big, really fast SSDs. So we can store that stuff off GPU and then transfer it in when we need it. So just one of the like random speculations that people are betting on right now.
Yep. Yeah, and you'll hear people talk about quadratic scaling because right, the queries times the keys. If you have 100,000, it's 100,000 times 100,000 that you need to multiply. One of the things that's interesting as a shortish term thing is that the quadratic scaling actually means that you get a significant benefit from anything you can do to reduce the sequence length. Okay, so Ryan talked about tokenization. Mostly after attention is all you need and ChatGPT came out at the end of 22, people weren't really thinking about tokenization. But one of the research areas that I think has heated up in 26 this year is you're going to see a bunch of papers where people try alternative tokenization schemes. Because if you can cut the tokens down by a factor of just half, it's going to cut this quadratic thing into a quarter. And so if OpenAI is spending $50 million every hour on GPUs, cutting that to a quarter saves them $37 million an hour. So it's not going to solve Ryan's thing longer term of you want to go to 100 million, that you need SanDisk to deliver you some kind of new memory or whatever. But it does in the short term potentially, save these big companies millions of dollars. So people looking at alternative ways of doing attention, doing less attention, do it only a quarter of the layers instead of all the layers. Again, a quarter of the layers gives you gives you a quarter times, 4 times, reduction in cost. Cut the tokens in half gives you a 4 times reduction in cost. So there's a lot of these things that we're going to see that are not necessarily mathematical breakthroughs. They're just do it a little bit smaller, do it a little better.
Yeah,
You want me to repeat it?
I can summarize it. So the question was like, why can't you just throw some of the KV cache away? So the LLM, it's processing all of this text, it's embedding it, and then you get this cache that's growing. But you have all of this stuff inside of it that's probably not relevant. You have all the times that there's the word it, like all of these little connector words that probably aren't that important. So there's there's a bunch of work that's being done on that right now in terms of like KV cache compression and pruning. So one of my coworkers just published something called KV Zap, and the whole focus is basically like how do we losslessly compress the KV cache? Because exactly what Ted's saying, like if we can just kind of like prune the history or compress it in some way, then that saves us so much. It makes things faster. It makes things take less memory.
Do you know what technique they used to?
It's called KV's app. I
Okay.
don't.
I'll look it up.
Yeah, they gave a presentation to us, but I don't know it well enough to really describe it. Yeah.
Yeah, so like the super earliest thing somebody tried was, oh, I'll just take every 16 and average them, and that'll cut my memory by a lot. But then it works to a certain degree and doesn't work, so like when you have this really large code base and the variables defined in only one place, then you really you risk, oh shoot, I lost that one thing I really need. So I think it's also possible we might see this bifurcation that a lot of researchers, they do a bunch of coding, and so you need this kind of precision. But maybe if you're just asking Chat GPT about like, my car is making this weird sound, maybe you don't actually need such precision, and you can prune, average, condense, summarize, zip up the KV cache. So there might be some knob you can say like, hey, I want you to charge me less, and just use this mode because I'm just talking about something easy, versus, oh, I want you to write a new web page for my application. Now I need you to be in like aggressive full mode. I can't have you make mistakes.
I don't know if I can find it, but this is their work. Basically, they set up a sort of leaderboard benchmark task saying how well can we compress this, and the trade-off that they're going for is like we want to get rid of as much of the garbage in the KV cache as possible, but we don't want to lose performance. Like how do we reduce this while not losing information? So very interesting area of work, but it's kind of still just in the works.
Oh, and also one note, in layer one of the model, you can say that the word "the" is probably very little information contained, but you have a model that's 48 layers, and it might actually be the case that in layer 39, the position where "the" is has like a bunch of sentence information encoded in it, and you can't as easily throw away that KV cache at layer 39. Whereas at layer one, it's probably a lot easier just to say like, the of comma. Maybe I can just maybe for coding comma not, but like certain things, I can just get rid of a lot more. You do have to think about, there's a KV cache for every link, and the deeper you go, the more wider of a view it has. And so with that large receptive field, you can no longer say that, the or whatever, because some of the research, you see things like periods at the end of the sentence actually contain a whole lot of summarized information about the sentence that came before and things like that. So it's a little trickier than it might seem if you're just thinking about the first layer, the raw words. Anything else?
Was there one online?
Oh yeah, I saw a hand raised.
Yeah, I had raised my hand, Ted, but you just addressed that about the multiple layers. I was
Awesome. Yeah, you caught that. Yeah, thanks for catching that.
All right, awesome. Thank you, everyone.
Awesome. Thanks again, Ryan.
Thank you, Ryan.